Well, hello there. Glad to have you back with me here again. Today we're going to be discussing displacement, speed, and acceleration. When we get done today, you're going to understand that acceleration is a vector quantity. Acceleration is the slope of a velocity time graph. Displacement is the area under the curve of a velocity time graph. And constant acceleration allows for kinematics to work. Well, what is acceleration? Acceleration is the change in velocity over time. Acceleration is the change in velocity, which includes direction. So it's a vector quantity. Remember, a vector quantity, as we've discussed prior to now, is a vector quantity is anything that has direction and magnitude. Put a little A in there for magnitude. There is a acceleration. You can be accelerating at 10 meters per second squared north. So it is a vector. You're going to include direction and time. So you are accelerating if you're just simply changing direction. So if you had your speed control on cruise control set on your car and you were going around in a circular track, you would be accelerating the entire time because you would be changing direction. So your velocity would be changing. You'd be changing direction. First example of this is we have a boy that's running 4.5 meters per second. He stops when his mother calls in 2 seconds. Well, what is this acceleration? Well, I'm going to make a little list. This is the information, and it says he stops. So his velocity final is 0 meters per second. His velocity initial is 4.5 meters per second. And the time is 2 seconds. Well, I've went through here and went ahead and worked it out. I used our equation here for acceleration, and I said his final velocity was 0. His initial velocity is 4.5 meters per second. The time was 2 seconds. So when you divide this out, you get 4.5 divided by 2, or 2.25 meters per second squared. Now, there's one thing I did leave out, and that is the fact that this is negative, because it would be 0 minus 4.5. So this would be negative. Now, this negative is simply there to tell us his direction, meaning the acceleration was in the opposite direction he was heading. If you have a negative acceleration, it means you're slowing down. So it means his speed is decreasing. Let's go on to the next one. Car is rolling 45 meters per second. It stops, and it hits a parked car and stops in 0.2 seconds. So my list is 0 meters per second because it stops. Its initial velocity was 45 meters per second, so this one was going about 90 miles an hour. And the time is 0.2 seconds. I want you to go ahead and try working this one out, and we'll see how you do. Well, as you can see here, I went ahead and worked it out. 0 in for the final velocity, 45 in for the initial, divided by 0.2, and we got an answer of 225 meters per second squared. And again, it would be negative. So this person's car slowed down fast, incredibly fast. Here, we just did some simple math. If we were to take this equation and multiply this both sides by t, just doing some simple algebra, the t's would cancel out, and we'd have at here. Well, in this case, if we would add vi to both sides, what that gives us here is vi plus at equals vf, and we simply rewrote it. And I want you to realize that the reason I've shown you this is becomes one of our kinematic equations. This is a very important one, and this is probably the more common way you'll see it written, as opposed to how it was we showed it to you to start off with. This is more of a ICP way of looking at it. The bottom one is how we're going to refer to it quite often in physics. Acceleration and displacement. I want you to understand how acceleration and displacement are related to each other. Now, some of you might be taking calculus and you've learned about the derivative. Well, if I were to take the derivative of this equation, what we get is VF equals xi plus 1/2 AT squared, and it's not really VF up here. I messed that up. This here ends up being XF. And, or you can just simply say, I don't care how you get it, Mr. Kimmel. But this is the equation of how displacement and acceleration relate to each other. Essentially what's happening here is we're dividing, for the most part, by time, not totally. But to a certain extent, we're dividing by time. Not totally, but to a little bit. Well, we have two equations that we've learned for distance now, or displacement. Not really distance, but displacement. And the first one was the one we had the other day. Distance or displacement equals velocity times time. In physics, we're going to quite often refer to that as XF. Your displacement, your final displacement, how far you've gone, is equal to your velocity times time. We just showed you, I forgot to put a plus sign in there, that your displacement when it comes to something that's accelerating at a constant acceleration is the distance that you were initially plus 1/2 AT squared. Well, if you put those two distances together, alright, if we put these two together, what we get here then is our final one. And this is our kinematic equation for displacement, and that's more specifically in a horizontal direction. It will change slightly when we get into vertical. Well, this becomes our equation plan. Our top one is one we will use for average velocity. The next one is VF equals VI plus AT. I want you to understand that we're going to use this when the story problem doesn't give us a distance quite often. That's when you're trying to find either the velocity, the acceleration, or time. Distance is not a component. The next one, notice that time is not in here. So if we don't have time, if they don't give us time in the story problem, we can still find the displacement, we can still find the acceleration, and we can find the velocities. The one I just showed you would probably be the one I would advise you to try using last. Alright, I pointed that out here. I would try using that last. Alright, I'm going to go ahead and show you how we'll use this. The first thing I'm going to do is make a list. Okay, what I've done here is I've went ahead and created a listing here of all the important information here. If the runway, can this airplane reach 27.8 meters per second for takeoff? Well, what I want to know here is, can I use one of my equations and this vehicle accelerating at 2 meters per second over a distance of 150 meters get to 27.8 meters per second? Well, I'm going to, notice it doesn't give us a time. There's no time in here. So what I'm going to do is I'm going to use our kinematic equation that doesn't involve time. And I'm going to plug information in. Now, as I've worked through this, I used my equation that didn't include time because nowhere up here did it give me a time. I plugged the information in. Initial velocity started from a stop, so that the initial velocity was 0. We like zeros. You're going to really come to like zeros. The acceleration was 2 meters per second squared. The total displacement was going to be 150 meters. Once you multiply, I get the VF squared equals 600. I hit square root and I get the final velocity is 24.5 meters. Now, it says, if not, what is the minimum length it must be? I can use that same equation now and say, okay, now I'm going to put the 27.8 squared, 0 squared, plus 2 times 2. And a lot of times I just simply put an x for that displacement and solve for x. I'm going to let you go ahead and try that for tomorrow. Alright, I'm back. Hopefully you've worked that out. No, I'm not giving you the answer. It's a simple algebra problem. We can work that out tomorrow if you have questions on it. What I want to go to now is understanding speed time graphs. And this is different than yesterday. Today we have speed and time. The other day we had displacement. This over here on the left was displacement. Today it is speed and time. But what we find out then is our equation, and I'm going to change this here. Alright, now I'm back. Made a few changes on here. I don't know why I made those mistakes, but I must have been in a hurry when I did this last time. What is the average acceleration of the object? Well, that is going to be our trend line right here again that we talked about the other day. Because the trend line, or the slope of a speed time graph, is acceleration. So all we have to do is identify our ordered pairs and find the slope. Okay, what I did here is I found two ordered pairs. I went through here and found 6, 6, and 8, 8. I plugged them into my slope equation, got 2 over 2, and I found out that the average acceleration of this object was 1 meter per second squared. So that's my trend line. Number 2, what is the instantaneous velocity of this object between 7 and 8 seconds? Well, I want to point out that this is now right here. That's a flat line, which means it has no slope, which means the acceleration, it's not accelerating. So we go straight over here and saying between 7 and 8 seconds, its speed was 8 meters per second. The last thing I want to discuss with you. Is displacement. Displacement can be found on a speed time graph. And the way we find the displacement on a speed time graph is we find the area underneath the curve. And that's one of the most important things here. And that was one of our things we wanted to learn today. So I've made this pretty simple for us. It says, what is the displacement of this object between 4 and 5 seconds? Well, that would be then between these two time frames. So I'm going to be finding then the area underneath the curve there. So there's a couple things we can do. I'm going to break this into two triangles, even though it's not exact. It does give me a pretty rough estimate. The base is 1. My height here is 4. So the area here is 4. And then I have a triangle that has a base of 1 and a height of 1. So that's 1 times 1 divided by 2, or half. So my displacement is adding those two areas up. Gives me 4.5 meters. The important thing here is I want you to know that if we want to find acceleration, we got to find the slope. If we want to find the displacement, then we have to use the area, which is what we did right here. So there's two different things we can find off a speed time graph, and that's different than a distance time graph. We'll talk more about this tomorrow. I'll catch you on the flip side.